So here's a nice flow chart that goes kind of through the thought process you have to put together to name a compound. Okay, so the first thing, the two types of compounds we focused on are ionic and molecular. They're usually pretty easy to tell apart. Molecular are composed of nonmetals. That's most of what we've been focusing on with Lewis structures. We also call these covalent compounds. They're sharing electrons. Okay, so examples would be things like water. Those are two nonmetals. Carbon dioxide. Oh, I kind of gave the name already, so you get the idea. CCl4. Okay, nonmetals. We've also talked about ionic compounds. They're typically either a metal cation. Okay, so something like, say, sodium +1 with a, it says monatomic there, but so a non-metal anion, something like chloride. Okay, or it could be a polyatomic anion, something like nitrate or carbonate, something like that. Okay, and we really only focused on one polyatomic cation, which I've kind of written over there, but you can see it there. NH4+, that's ammonium. So you could have, say, NH4+ combined with something like NO3-, and that would be an ionic compound. We would have a cation and an anion attracted by what we call electrostatic attraction. Electrostatic, see if I spell that right. Attraction. Okay, so that's the first thing you have to do. Is it ionic or is it molecular? Okay, molecular is pretty easy to pick out. Two nonmetals. And they're actually the easiest to name, I think. So let's do molecular first. Let's start here. So composed of two nonmetals. What do? We use prefixes. And I will show you what prefixes we use in just a minute. You can see here that one of them is mono. That means one. It's, it says usually omitted, but let's admit it. For the first element, if there's just one of the first element, like in CO2, we don't say monocarbon dioxide. We just say carbon dioxide. And by just saying carbon, it's understood that we just have one carbon in each molecule. Okay? The ending of the second element is changed to IDE. So oxygen in this case becomes oxide, carbon dioxide. Chlorine would be changed to chloride, and so on. Okay? So here are your prefixes. Let me scroll down. I have a table here. Most of these you'll be familiar with. Mono, di, tri, 1, 2, 3. Tetra might seem odd at first, but if you know Tetris, if you think about all the Tetris shapes, there were always 4 blocks. Okay, so 4, tetra, 5, penta, hexa for 6, hepta for 7, octa 8, nona for 9, and deca for 10. And we're not going to go past 10. Okay, so let's do a couple of examples of molecular that you'll be familiar with. Let's do some easy ones. CO, carbon. We don't say monocarbon. We just have one of those for the first one. But we do have to say we have one oxygen. Monoxide. We change the ending to IDE. As opposed to carbon dioxide. Okay. All right. I wrote this up above. CCl4, carbon. Again, not monocarbon, but just carbon. 4, tetra. Not chlorine, but chloride. Again, we change the ending to IDE. N2O5. Bunch of examples here. Dinitrogen. And then 5 is penta. Now, sometimes we don't put, and I won't be that picky, I won't take off for this, but sometimes, sometimes we do, sometimes we don't. This is where it gets interesting. Do we say pentaoxide? Technically not in this case, we just say pentoxide, but I'm not going to take off for that. So if you write pentaoxide, so sometimes we drop one of the vowels when we put these together. And then let's do one more, P4S10. Okay, 4, tetra, phosphorus. And 10, deca, sulfur becomes sulfide. All right, so I think molecular compounds are really easy. It's just say how many you have using these prefixes that you should be more or less familiar with. All right, so that's covalent molecular compounds composed of nonmetals. Now, ionic. We have to break ionic into two categories. And the reason why we need to do this is because there are certain cations that only lose a set amount of electrons. The alkali metals in group 1, okay, so group 1 of the table, will always lose one electron and form a +1 ion. Okay, so for example, sodium +1, potassium +1, losing one electron. Okay, and we've talked about this already. Group 2, they're always going to lose 2 electrons when they form an ionic compound and form a +2 ion. Things like magnesium 2+ or barium 2+. Okay, so those are always going to be the same. And there are some select other ones. Silver +1, aluminum is going to lose 3 electrons and form a +3 ion. Cadmium 2+, zinc 2+. Make sure you know aluminum. I'm not so worried about silver, cadmium, and zinc, but aluminum will lose 3 and form a +3 ion. What that means is that, for example, sodium, and I'm going to scroll down and get myself a little bit more room down here. Say when it combines with chloride, okay, so chlorine's in group 7, it's going to gain 1 electron to achieve a noble gas configuration. We form NaCl, and that's the only combination of sodium with chlorine. That's it. There isn't another ionic compound where they're combined in a different ratio. In this case, it's 1:1. That's the only ratio they'll combine. Same thing if I take aluminum 3+ with chloride. Okay, it's always going to be AlCl3. Okay, because we need 3 times -1 to balance the +3, and so on. Okay, now let me just show before we name these as saying that these are the only chloride compounds that exist for sodium and aluminum. For iron, for example, there is both FeCl2 and FeCl3. So we're going to have to do something a little bit different with those because there's 2 different iron chlorides. There is only 1 sodium chloride. There is only 1 aluminum chloride. And that's because the alkali metals will always only lose 1 electron and form a +1 ion. Aluminum will always lose 3 electrons and form a +3 ion. So it's going to be fixed what those ionic compounds are going to be. Okay? And if that's the case, all we say is the first name, sodium, and again we change the ending to IDE, chlorine becomes chloride. Okay? AlCl3, aluminum, chlorine becomes chloride. That's pretty darn easy. Okay? We could do another example, since we're kind of stuck on aluminum and sodium. What about with oxygen? Sodium's +1. Oxygen is in group 6. It's going to gain 2 to achieve a noble gas configuration, forming a 2- ion. So we're going to need 2 sodium ions. And so when we write the formula, we're going to just leave the charges off, Na2O. For aluminum, 3+ with oxide, O2-. Cross our numbers here, 2 aluminums, 3 oxygens. 2 times +3 is +6. 3 times -2 is -6. That gives us Al2O3. Okay, those are the sodium. If we say sodium oxide, that is the only sodium oxide. If I say aluminum oxide, that is the only aluminum oxide. And therefore, I can just, as I just said in naming these, Na2O is just sodium. Oxygen becomes oxide. Aluminum, oxide. So those are easy, but you do have to then distinguish first that it's ionic, metal with a nonmetal, metal with a polyatomic ion, things like that. So once we know it's ionic, you then have to say, well, is it one of these special cases where the cation only can have 1 possible charge? The alkali metals are always +1 in an ionic compound. They will always lose 1 electron. The alkaline earth metals are always +2. They will always lose 2 electrons. And then there's a few select other ones. Make sure you know aluminum will always lose 3 and form a +3 cation. All the other metals which is basically all the transition metals for the most part, almost all of the transition metals, and then some of the metals that are below the nonmetals, they will form various what we call oxidation states, various charges. Okay, there's not just one fixed charge. Okay, so we must specify the charge on the metal cation. We must specify. Okay, make sure you note the difference. Alkali metals are always +1. We don't need to specify that. We know that. Alkaline earth metals are always +2. We know that. We don't specify it. But here's two compounds of iron and chlorine. We need to specify the charge on the iron. How are we going to do that? Okay, well, the first thing we have to do is figure out what is the charge on iron. And how do we do that? We look to the anion. Chloride, being in group 6, is going to gain 1 electron to form chloride. Okay, so I have, in this case, 2 times -1, which is -2. So this iron cation must have a +2 charge. 3 times -1 is -3. This iron cation must be +3. Okay, so more often than not, we're going to have to figure out the charge on the metal cation from the anion. Okay, so that's the first thing we have to do. And then once we know that charge, we are going to specify it. How do we do it? We use a Roman numeral in parentheses. So this first one becomes iron 2 chloride. Okay, now the 2 is not specifying the 2 on the chlorine. It's specifying this +2 charge. And I'll show you an example where you'll see that you're actually not specifying the subscript, because this one, you might think, wait, it looks the same as the subscript, because this one's going to be iron 3 chloride. Okay? Exciting, huh? So, ionic compounds. Some cations only have one possible charge. We don't specify it. Most metal cations are going to be able to have more than one possible charge. They're going to form more than one type of ionic compound with the anion, in this case chloride. There are 2 different iron chlorides, so we have to call one iron 2 chloride +2, one of them iron 3 chloride +3. There you go. All right, let me show you another example where the subscript doesn't match up. So here are 2 more examples. Now remember, we can have polyatomic cations. So this is titanium Ti combined with carbonate. And there's another one. Okay, so there's 2 different titanium carbonates. We have to specify the charge on the cation. If I just said titanium carbonate, it'd be like, which one? There are 2 different ones. Which one is it? So how do we figure out the charge on titanium? Look to the anion. So carbonate has a -2 charge. I believe I gave you a list at some point that you should know. If I didn't, when we get to class, look these up in the book for now. There will be a table in Chapter 3 that shows the charges of the ions. But remind me in class and I'll give you a list of the more common ones you should know. So carbonate as a unit is -2. So titanium, since it's 1 to 1, is going to be +2 in this compound. Okay? So remember, CO3 as a unit has a -2. This one we have 2 carbonates, each at -2, for a total of -4. So titanium in this one is +4. Okay? So we've practiced this before. We wrote formulas and assigned charges. We just didn't name them. So we've practiced some of this before. So now, again, we're going to specify the charge on the cation, not the subscript of the anion, as it kind of looks like up in the top example. So this first one is going to be titanium 2 carbonate. plus 2. We use a Roman numeral 2 to specify that. So this has a plus 4. This one is titanium 4 carbonate. All right, plus 4, Roman numeral 4. Okay, you see that that does not match the subscript of the anion. It's the charge, cation charge, that we're specifying. All right, that's all there is to naming compounds.